Another IAEI News Live. My name is Thomas Dimitrovich. Just want to make sure we are going. I believe we are. All right. Just checking. Okay, so welcome to another IAEI News Live. Thomas Dimitrovich here. Today, we're going to continue a series and look at that small one-line diagram that includes two transformers, which I think which is critical. And the reason I say that is because the math that we're using, this is going to help you understand per unit, and it's going to help you understand complex variables. And we are going to calculate short circuit currents by hand, and it all starts now. All right. Okay, so hopefully you have you've been with us here for a little bit. We did some work over the last couple of hey, I'm on, David. Thanks for joining. I am hopefully I'm on Facebook. I see I'm on YouTube. I just got to double check Facebook for some reason. Been having a couple issues. Yeah, we're live on Facebook too. All right, so we are golden. Everything's good. So let's do this. What I want to first do is cover where we were. We're going to write down some basic fundamental equations that are important for calculating fault currents by hand using a per unit method. Now, the per unit method is a per unit and complex variables, two very important tools for any power systems engineer to understand. Complex variables, trigonometry. If you're into trig, or if you took trig classes, trigonometry classes, triangles, power triangle, power factor, those equations are critical. We will write all of those equations down so that you have those. Also, complex per unit. Per unit is a way for an engineer to model a power distribution system. And per unit is a tool that we use, especially when you have multiple, hey, Costa Rica in the house, when you have multiple voltage levels in a power system, dealing with resistance values and impedance values is very difficult. And the reason it's difficult is because I can't add a resistance value that's on a 240 volt system to a resistance value that's on a 480 volt system. I need to transpose resistance values all to one voltage level and then transpose things back to the different voltage levels. That is very complicated math and very easy to make mistakes with. So what we use is what we call per unit, and per unit lets me add all of my impedance values together because they're all percentages of base values. And I'm going to walk through what those base values are, how we calculated those for this power distribution system. It's a small system, and we're going to do that right now. So let's take a look at what our system is. We're going to start with an infinite bus, but if we've got time, I will take the, we'll assume an available fault current on the primary of this transformer from the utility, and we'll convert that to a per unit impedance, and then we will see what it does to our fault current calculations. Because once we have the per unit values calculated, we're happy boys and girls. So we have a 1500 kVA transformer, 4160 to 480, 5.75% impedance. Now, what I did in these equations, I just used 5.75%. You should do a 0.9 to all of these values from a transformer percentage perspective. I didn't do that. I'm just telling you right now that you should do that. So, but I just didn't want that added complexity. Because I wanted to model this in SKM as well and get that done. Oh, Oman in the house. Abdullah, thank you for joining. Mr. Hofkin, thank you for joining as well. All right, so then we have 6 400 kc mil at 6 in parallel, copper in steel conduit at 10 foot, feeding a 2000 amp panel board or switchboard, whatever, it doesn't matter, because we're not looking at overcurrent devices yet. And what we'll do is we'll do arc flash calculations in maybe one of the next sessions. For 3-aught conductor copper steel conduit 250 foot feeding a 500 kVA transformer. And that 500 kVA transformer has a 3% impedance. And again, I'm using that straight impedance for the reasons I stated before. Then we go off of the secondary 350 kc mil copper steel conduit 10 foot to a 1200 amp panel board. So that's our system. And what we did last time, which I'm going to walk through these calculations, and I took that video down because I have an error, and I'm going to show you what the error is, and I'm going to re-record that that math, and it's a fundamental error that I made 2 mistakes last week. We are not infallible, so let's do this first. Let's do our equations. Add a page. Let's talk key equations. All right. Now the first thing we need, I'm going to do it in blue, we need our complex variables. And remember, complex variables, Nihad El Sharif in the house, and complex variables. And Nihad's one that caught one of my errors. He called me, he says, hey, Tom, you had a numerator and denominator flipped, and that's the story of my life. All right, so you remember our triangle, and we have R across the bottom. We have JX, and we use J to indicate an imaginary number, J, and that indicates the vertical axis as our impedance. And then our reactance. And then we have Z. Now, the basic equations that we have for, hey, Joe Ballard, how are you, buddy? Good to see you. Good to see you. So our basic equations. I can't see it, Joe, but I can see your name pop up, just like I can see Abdullah from Oman. All right, so Z is equal to R squared plus X squared, the square root of that. So that is Z, that's the hypotenuse of Z triangle. Oh, we forgot an important piece here. Theta, that is our power factor angle. Okay, so I got Z. How about R? Oh, let's talk theta. Theta equals A tan, or you may have seen it represented as tangent to the -1 of X over R. That gives us our angle. Warning, access to internet applications has expired. I'm going to take this out so you know A tan is an inverse tangent. It is a button on your calculator. It should be. You could have a simple calculator that doesn't have these cosine, sine functions. You need the scientific calculators, just saying. All right, so R. What is R? R is equal to the magnitude of Z, and we indicate magnitude by putting the 2 parens in front of it. Cosine of theta. And then X is equal to the magnitude of Z sine of theta. Those are the important equations that we need to know for complex variables. And once you know any 2 of those, right? So if I know the angle, if I know X to R, that ratio, I would do an inverse tangent and get theta. Now I know theta, and I know the X to R ratio, and I know the the angle, I know the X to R ratio, I could calculate everything else. So you just need a couple data points. All right, so what else? All right, so that's it for complex variables. How about per unit? So per unit, so a value per unit is equal to actual over the base. That is a very important piece of the puzzle. You've got to know all of your base values, but it's a percentage. So if I had I actual over I base is my per unit, multiply that by 100%, then I've got a percentage, just like you see on transformers. So per unit over actual. So the other thing we need to find is what? So let's do this. You have assume a kVA base, right? So you have to calculate, you have to establish a kVA base and equals a kVA, and you can pick that value. You have to calculate your I base is equal to a kVA three-phase base divided by the square root of 3. That's an ugly looking 3. Divided by, divided by the square root of 3 times kV three-phase. All right, so that gets us an I base. And remember, our Z base is equal to V base over I base. And I'll make this a line to neutral voltage base value. That's how we get to Z base. And how do I know that? V is equal to IR. And I want to find I, so I take V over, I want to find R. I take V over I is equal to R. So that's how you come up with that. And that's a magnitude number. That is a magnitude number. Another important equation. Let's do this. Another important equation is I'm gonna find my notes, because add, and I'm going to do a kind and presentation. All right. And I'm going to add last opened, then the last 20 days. All right. Single line impedance diagram. I'm just looking for my notes. Well, another important thing to reference is another document. This is a book that I find very helpful. This is my Beeman handbook. My Beeman handbook it's what is it, 1950s vintage, but it's got a section in here with all of the different equations. So I want to make sure I get this one right. All right, so my kVA base is whenever you have I have a 500 kVA transformer in this application. I'm going to pick a base of 1500 kVA. Now that 500 kVA transformer has an impedance of 3%, but it's based upon 500 kVA as a base value. I need to convert that 3% impedance to the new base, which is 1500 kVA. And how I do that, I take the old impedance, that 3%, multiply that by the new kVA base divided by the old kVA base. And I just want to verify that equation. There we go. Yeah. And that's what it is. All right, so where's my key equations? I'm going to add another sheet here. Add a page. I'm going to do per unit on this page. This is what we do. We copy this, and we're just going to move it down. All right, so we're going to call this Z per unit 1 equals Z per unit 2 times kVA base 1 divided by kVA base 2. Make sense? So what that does is, if my kVA base, I'm just going to call it kVA base. So for that 0.03, so I'll just do an example. 500 kVA transformer, 3% impedance. I take my Z per unit is equal to that 0.03 per unit, because I take the 3%, divide that by 100, times 1500 divided by 500. And I'm going to use this as my calculator. So I take 0.03, 1500 times 500, divide, and that is 0.09 on a 1500 kVA base. So what I just did there, and you have to make sure, this is an important part of per unit. And it's something that people, engineers miss on exams. It can get confusing. In fact, this equation, I screwed this equation up. I had, last week, I had 500 over 1500, I believe. I'd have to go down and take a look at the math, because this is the same sheet I was using. That can get you into a world of hurt. So make sure, hey, good ETZ afternoon. Just tuning in, hypotenuse, need more coffee. That's right, Earth Electric. Hey, Felix, great to see you. Jody, wages. Yes, we're getting to high-level math, buddy. All right, so those are my key equations. You need to know these. You also need to know your per unit equations. All right, and for now, for what we're doing, all I need are the how to get the Z per unit of a transformer from one kVA base to a different kVA base, to the kVA base that I selected. All right, so let's walk over the base values. Let's do the math on the base values. So I already said I base. Yes, I base, Z base is V base over I base. So remember that each of these voltage levels are going to have their own base values based upon the kVA base that I selected. And the kVA base that I selected is 1500. Why did I pick 1500? Well, I don't have to do any math for that transformer. I don't have to convert 5.75% Z, which is already on a 1500 kVA base. Remember, that 5.575% is a per unit value already. The manufacturer did that for you. But it's based upon the kVA base of the transformer, which happened to be the same kVA base that I picked. So all of my base values for the 480 volt side is going to be based upon 1500 kVA, a 480 volt base. I get an I base of 1804. I get a Z base of 0.1536. Okay, and remember, Z base is this value right there. I'm just going to do the math. Is 480 divided by the square root of 3 to get to a line of neutral. Divide that by 1804.2. And I'm just going to do the math to make sure. 480, divide that by the square root of 3. And divide that by 1804. 1804.2 divide is 0.1536. That's how we get Z base. Right? And that's important. Why is that important? Because when I look at conductor number 1, or this conductor number 2, I need to take the resistance and the R and X, which I'll get from the 2023 code book. I'll get that from the code book. Table 9, Chapter 9, Table 9 gives me my real and my reactive components. And then I divide that value by the base, and I get, because that's actual, right? So I take my and I'll do this. Let's take a look at conductor 1. Conductor 1 is right up here, right on the secondary of this transformer. There's conductor 1. So what did we do for conductor 1? We had 6 400 kc mil copper, steel, 10 foot. We went to chapter 9, table 9, and I got a resistance and a reactance at ohms per 1,000 foot. Ohms per 1,000 foot. So I got 0.035 plus J 0.049. That's my triangle. Right? So that's my triangle. The R is there. The X is there. And then I converted that to polar coordinates. How did I do that? Let's go back up to my equations. I took my X divided by my R. I took the inverse tangent. And that gives me my angle, and my magnitude is r squared plus x squared, the square root of which. So that's what I did for conductor 1. I took that value and that value, I squared them together, added them, took the square root, I got 0.0602. The angle is a tangent of X over R, and that is all still on ohms per 1,000 foot, but I only have 10 foot of that. So I have to take 10 over 1,000 and multiply it by that number, which I did right here, 10 over 1,000, multiply it by that number, and I get 54.4623 ohms. That is Z actual. Eastern time zone. All right, David. All right, so Z actual. And how do I know what is per unit? Is Z actual over Z base right here. So Z actual is 0.0006 at an angle of 54.4623. So I take how did I get to 0.0001? It's because I have 6 in parallel. So I have to divide that by 6. And that gets me 0.0001. That's my actual ohms. Not per 1,000 foot. That is my actual ohms for that 10 foot of conductor. I take Z actual, which is 0.0001, divide that by Z base, which is 0.1536, And this is my per unit impedance for that first conductor. So it's a lot of math to get to that value. Now, conductor 2, where's conductor 2? Conductor 2 is still on the 480 volt side. I still use the same base values. I'll still use the 0.1536, and I believe here is where I made a math error. I did. I made the math error, and I'm going to fix it here. I didn't want to fix it until we were together. So 0.079, 0.052, 0.079, 0.052. Hold on. 0.079, 0.052. I'm going to call up my calculator. There it is. All right, so I have 0.079 and 0.052. I have to square those, add them together, take the square root. So I take 0.079 squared, 0.052 squared, so it's 0.0062. I have to add that to 0.0027. I add those two together, and then I take the square root. It's 0.0946. 0.0946, and I don't know how I got 0.5327, but I did. 0.0946. So let's take this out. .0946. And I'm going to write in red 0946. The angle is still good. Now, if I take 0.0946 times 250 over 1,000, because there's only 250 feet, I get 0.0946. 0.0946 times 250 times 250. Divide that by 1,000. 0.0236. So instead of 0.1332, I should have 0.0236. So 0.0236. All right, at an angle of 33.5354. Divide that by 4. 0.0236, divide that by 4 is 0.0059. So this should have been 0.0059. At an angle of 33.354. And then I have to divide that 0.0059 by the base, 0.1536, and I get 0.0385. 0.0385. So what did I just do? I took conductor number 2, which is 4/3/0 copper steel, 250 feet. I went to chapter 9, table 9, 0.079, 0.052. I got that into polar coordinates. Then I divided that by, multiplied that by 250 over 1,000 to get to only 250 feet. That's my ohms for 250 feet. And then I divide that by 4 because I have 4 conductors in parallel. And that gets me to 0.0059. That's in actual ohms. And then I got to divide that by base, my Z base, to get it into per unit. And that is my per unit value, 0.0385. And then I can convert that to rectangular. How do I convert it to rectangular? R Z times cosine theta is R. Z times sine theta is X. And that's what this is. Whoa. So the R is equal to the magnitude of Z cosine theta. X is equal to the magnitude of Z sine of theta. And that's basic trig. Piece of cake. Is there a new edition of the Brown book? And where do you find theory books? Willie Snyder. So they're working on the color books. They're dot series. I don't believe the brown book is done yet. But in my opinion, the red book and the buff book, all you need. I don't care what edition it is. You know why, Willie? Because physics hasn't changed. Complex variables hasn't changed. Per unit hasn't changed. It was right in the 50s. It's right today. That's what I love about this. You can find, in fact, the older books do a better job of explaining it. So I would stick to some of the older books. And the only thing I would go to new technology for is the actual values like R and X. You could go to the manufacturer and say, what is your resistance and impedance to calculate your values? But math is math. All right, so transformer 2. Here was another mistake I made. Look at that. All right, so KVA new over KVA old. So what I did was I did 500 over 1500. It should be 1500 over 500. All right, so I'm going to just clean this up. 1500 1500 over 500. And why am I doing that? Because the impedance, that 0.03 per unit, which is 3% divided by 100, is based on a 500 kVA base. And I'm doing this entire system based upon a 1500 kVA base. And I'm telling you, if you're taking your PE exam, I don't know if this is going to be on there, but I think it's probably going to be on there. You got to know this type of math. That if they do base values, you got to know how to convert the impedance values onto your new base. Please don't forget that. So 0.03 times 1500 over 500 is 0.09 at an angle of 90 degrees. Let's get rid of all of this. All right, so those are our base. Oh, and then we have one more conductor, conductor 3. We have 4 350 kc mil, copper steel, 10 foot. This is out of table 9, chapter 9, ohms per 1,000 foot. I got to multiply that by 10 foot over 1,000, and I get 0.0006 at an angle of 52.02. I divide that by 4 because of 4 conductors in parallel, and I get a ohms value of 0.0002 at an angle of 52.05. I have to calculate that on the new base, but why did I use 0.0288? I'll tell you why. Because remember, this base value of 0.1536 is only applicable at the 480 volt level. When I go to the secondary of this downstream device, I'm at 208 volts. So I have to calculate, I have a new voltage base. That means I have a new I base, which means I have a new Z base. Capiche? So my Z base is now 0.0288 because I have a new voltage base and I have a new I base. My I base is 4163.6. My voltage base is 208. And I calculate my Z base by taking voltage line to line divided by the square root of 3 to get the line to neutral, and divide that by 4163.6. 4163.6. That's my new. So remember, even though you pick a KVA base, and one of the things that I always would forget about in school was that when I go to different points in the system, my voltage changes. I don't always use 4160 or 480. When the voltage changes, that means my I current has to change, and that means my Z base has to change. So everything is put on a 1500 kVA base, but I still have to calculate different currents because I'm at different voltages. That is a very important thing to remember in per unit. I would typically screw that up. It just escaped me I mean, you know, you're nervous, you're on an exam, you're in a test, you gotta relax and just think about the basic equations. All right, so my new base for my Z base at the 208 volt level is 0.0288. So let's go back down. So that is why I used 0.0288 to get a 0.0052. Now, let's just convert this. 0.0052 at an angle of 52.05. I want to turn that into an R plus JX, right? So remember, R is equal to Z cosine theta is equal to the magnitude 0.0052 magnitude times cosine of 52.05 degrees, right? So let's do this. 0.0052, 52.05. 0.0052, 52.05 cosine multiply 0.0032. So R is 0.0032. X is equal to the magnitude of Z times sine of theta equals 0.0052 times the sine of 52.05 is equal to, gosh, you've got to love this stuff. 0.0052, 52.05. 0.0052, 52.05 sine times 0.0041. 041. So that is in polar coordinates. Rectangular coordinates, I have 0.0032 plus J 0.0041 per unit. That is the cat's meow. All right, so now here's the next thing. Now we have the impedance diagram. So what we are doing is we're converting a one-line diagram into an impedance diagram with all of our per unit values. So this is my 0.0575 at an angle of 90. This is my point, and remember what is my R plus JX on this one is 0 plus J 0.0575, right? So that is my R plus JX, and we're going to do that for each of these. And I already did it while I was away, and I would put them into a table for us. My conductor 1 is 0.0007 at an angle. My conductor 2, remember we fixed this one, 0.0385. 0.0385. So what I'm going to do is delete this. And I'm going to copy this and move that over there. And then remember, we fixed this too because we had the KVA flipped El Runo flipped Brunos. So this should be 0.09, 0.09 at an angle of 90 degrees. And then we have 0.0052. So here is our table. I have our polar coordinates here. I have our rectangular coordinates there. So for each of these values, this is my transformer 1, 0.0575, my R and my X. This is C1 at the magnitude Z and the angle. This is the R and the X. C2, 0.0385, 3354, 0.0385, 3354. So there's my 0.0322, 0.0212. There's my 0.09 at 90 degrees. And I have 0 at 0.09. There's my conductor 3, 0.0052 at an angle of 52.05. So there's my per unit values. And these are the totals. So let's now, when we add, and this is why I do this table, when we add conductors in series, which to get the total Z, I have to add all of those conductors in series. And what do we know? When we are doing complex variables, when we add complex variables, we have to add the R's and the X's. They add. We don't do the polar coordinates. So I am going to do this separately. I want to make sure that I got it right. So what are all of my R's? 0.0006 plus 0.0322 plus 0.0032 plus is 0.036. So that is correct. Let's do the X's. 0.0575. That's that transformer, remember? 0.0575. 0.0004. 0.0212. 0.09. 0.0041. And that should be 0.1732. I got 2132. 0.1732. Check me. Let's do the adding again. 0.0575. 0.0004. Add that together. 0.0212. Add that. 0.09. Add that. 0.0041. Add that. 0.1732. All right, so that's my X and this is my R. So Z is equal to 0.0360 squared plus 0.1732 squared, square root of, I'm going to square that one, 0.036 squared plus square root 0.1769, 0.1769 at an angle of X over R inverse tangent. 0.1732, 0.036, divide, inverse tangent, 78.2581, 78.26 degrees. Now I'm going to use my calculator. I'm going to add these polar coordinates up. 0.0575 at 90. 0.0007 at 54.4623 angle plus 0.0385 33.354 plus 0.09 at an angle of 90 plus and 0.0052 at 52.05 plus, 0.1770 at an angle of 78.34. So this was wrong. So 0.1769 at an angle of 78.26. That's Z total. Now, this is what we're going to do. Now, remember, I am going now to get I'm going to delete this. I'm going to delete this. Right. I'm just getting rid of some stuff here. Now, Z total. So we know what Z total is. Let's do this. We're going to calculate fault current next. We have everything we need to calculate fault current. Copy, paste. So this is my total Z. Right, so all of this equals that. Now, what is I short circuit? Let's do this. Oh man, I'm excited. Add page. We are ready to calculate I short circuit is equal to I per unit times I base. Now, what is I per unit? I per unit is equal to V base. Nope. V per unit divided by Z per unit. We just calculated Z per unit. So we know Z per unit is 0.1769 at an angle of 78.26 degrees. Okay. Now, what is V per unit? Where are we at in the system? We are at the 208 volt system. So V per unit is equal to V actual over V base is equal to 208 over 208 is equal to 1. So my voltage per unit is 1. Right? Let's get rid of this. We no longer need this. So my I per unit, so I per unit is equal to 1 over that, 1 over 0.1769 at an 1 over 0.1769. 0.1769, 1 over, is 5.6529. 5.6 times 5.6529. 5.6529. At an angle of, remember, when we, complex variables, when you have 1 at an angle of 0, when you divide, you take the numerator in angles, the numerator minus the denominator. So the angle of this is minus 78.26 degrees. So that is my I per unit. What is my I actual? Equals I per unit times I base. What is my I base? I'm glad you asked that question. We got to go back up. What is I base at 208 volts? Ladies and germs, copy. You excited? I am. Paste. So that's I base. I per unit is 5.6529 times 4163.6. 5.6529 is already in my calculator. 4163.6. 4163.6. I'm going to do the multiplication. 23,536. 23,536. 23,536. Yep, 0.5. But we're not going to worry about the 0.5. 23,536. In fact, we'll say this is 23.5 kiloamps. So if I go back to my one-line diagram, let's go all the way up. That I short circuit is 23.5 kiloamps. Ta-da. All right. 23.5 kiloamps. So, my overcurrent protected device has to be greater than 23,000 amp interrupting rating. My equipment has to have a short circuit current rating greater than 23.5 kiloamps. That's my, now, let's do this. Let's do this. Oh, wait a second. Hold on. You know what we're going to use? What is my fault current on the line side of this transformer? So if I want to know the fault current at that point, here's how I do it. I add what's my base value? My base value of 480. 1804.2. 1804.2. If I want to know what I short circuit is right here, I take 1804.2, that's my I actual, divided by Z per unit. So it's T1Z per unit plus C1 per unit plus C2 per unit. Let's do it. All right. So I got to come down to my table. I have to take T1, C1, and C2. Calculator. I'm going to put a little line right here. And I'm going to add 0.0006, 0.0322 plus, and that is 0.0328, 0.0004 plus 0.0212, 0.0212, 0.0216, oh, plus 0.0575, 0.0575 plus 0.0791. Okay, so 0.0328, 0.0791. Point 0328 plus J 0.0791. Now, so that's 1804.2 divided by, now I have to take those and create the magnitude. So 0.0328 squared, 0.0791 squared, add those two together, square root, that's 0.0856 at an angle of 0.0791, divide that by 0.0328, inverse tangent, 67.48 degrees. So 1804.2, divide that by 0.0856, 0.0856 divide is 21,077 at an angle of negative 67.48 degrees. Now, why did I do that? So that is that I short circuit, right? So I know down at the end of C3 is 23.5. Right at the beginning of that transformer is 21,077. We're going to check our numbers. So what I got to do now is, hold on. I need to call this up over here. Lou Petrucci, you following me, buddy? You following this? Gotta find my numbers here. All notes. I'm gonna go up to the top. That's not it. Action items isn't it. Oh my goodness. How do I gotta get this so that I have it visible so I can see it to believe it. Unfiled notes. Oh my gosh. All right. So, and it's okay. So here's what we're going to do. I think I have the Busman FC Squared app. And what I want to do is I'm going to use the Busman FC Squared app and see where we are with that app. Next week, well, you know what? I might be able to do this. I do have SKM, and I did set it up in SKM. TD, okay. All right, Lou. David Castro. So here's what I think I'm going to do. And I'm going to bring this computer up. And I don't know how to do this, or if, I don't have that. So how would I do this? These are all connected. These are connected. How would I do this? Action items. All right, we had 23.5 kiloamps. All right. All right, so I love this stuff. I love it. I love it. I will show you what I got in SKM. If I can. I gotta have an app. Clean feed. Yes. Clean feed. All right, so ladies and germs, look at this. That says 23.482. 23.482. 23.5 kiloamps. All right, so what about this one? Whoop. Clean feed. Whoop. I don't have a touch screen, so whoop. Bear with me. I gotta go up. There's my transformer. 21,053. 21,053. What did I get? 21,053. 21,077. So, tell me that's not pretty doggone close. Tell me that's not pretty doggone close. Okay, so SKM got us to 21,000 amps. Our hand calculation, now that 21,077 versus 21,053, those are rounding errors. That's the detailed in math. So these numbers with the transformer involved on the secondary of the transformer, I got 23.5. Now what we'll do, time is it? 1 more minute. I can't do it in 1 minute. But what we'll do next time, what we are going to do next time is we will add the impedance for an available fault current, and let me know what available fault current you guys want to use, and that is what we will use. We will put the math in for an available fault current on the primary of the transformer. Maggie. All right, guys. There you go. That's my girl. Maggie, say hi. Don't you look at me. She's looking out of the corner of her hand. Hi. That's Maggie, everybody. Now you saw Maggie. All right. So we will add available fault current from the utility. We'll give you that equation and we'll rerun this calculation. We have the table. I'll clean up the table. Maybe I'll put it in a little spreadsheet or something. I don't know. But we now have the math. Hey, thanks, Joseph. We now have the math and we have the equations. What else? We got the math. We have the equations. We'll do the available fault current on the line side, from the utility, and we will add a motor. So I'll update this diagram to include a motor. I'll put a motor at the 480 volt level and at the 208. No, we'll just do the 480 volt level. But I'm going to keep things in small pieces. We'll add the motor at the 480 volt level. We'll verify our answers just like I did in SKM here, very close to those numbers. So now we have a model in SKM. We have this modeled here. We will put a motor in. We'll add the utility. And then what we'll do is we'll pick our overcurrent protective devices. We'll pick our overcurrent protective devices and equipment in another series, another session, and then what we'll do is we'll calculate the incident energy. Man, I just got goose pimples. Okay. I'm going to hop on another call, and thank you for joining in for another wonderful, fun session of IAEI News Live. We will see you next week. Thanks for what you do for the electrical industry. Thanks for what you do for electrical safety. Remember to be safe and please stay healthy. See you next week.